was line 22, 7b97z90, scanning beam trap, BEC, superfluidity, laser light, atom frequencies, 5G Wow Seti. There's the alien radio signal, September 19, 2013. Previous video was line 22, 7b97z89, harmonic magnetic dimple trap, optical dipole force laser lights, 5G Wow Seti. Today's November 24th. Okay. We're going to talk about blue detuned laser beam, velocity, trapping, frequencies of the atom's light potential. So, Googling atomic pulse equations, quotes and PDF file results are on a blog. Optical dipole force on ladder-like 3-level atomic systems driven by chirped fused cycle pulse laser fields from these scientists in June 2012. arxiv.org. The keyword was optical dipole force and quantum atom optics experimental projects from physics.uq.edu.au. Quote from blog, scanning beam trap. Figure 4. Image and cross-section of atoms in a line potential. The flat region in the cross-section is about 80 in width with 3% fluctuation in density. An area of great theoretical and experimental interest is the study of superfluid behavior in BEC. A defining feature of superfluidity is that it has zero viscosity. Friction is slow. The original analysis by Landau 1 for known superfluids such as helium, liquid helium, predicted the observation of a sharp onset of excitations when a microscopic impurity or obstacle was dragged through the superfluid above a critical velocity. For a dilute gas, BEC, this analysis predicts a critical velocity equal to the speed of sound in the condensate. To date, there have been a number of observations of the critical velocity in BEC. Too hot. Raymond et al. 2 used a blue detuned laser beam which they scanned through the condensate with the blue laser beam analogous to a microscopic obstacle dragged through the superfluid. They measured a critical velocity of 1.6 mm per s, a factor of 4 lower than that expected by the critical velocity being equal to the speed of sound in the condensate. With the magnetic trapping potential used, however, there was the added problem that the condensate does not have a uniform density, meaning that the local speed of sound varied across the condensate, making a reliable measurement of the critical velocity difficult. We have been investigating new methods that can provide a uniform trapping potential. The method we employ consists of scanning a red detuned dipole beam in 1D using the RF shift on a Husto optical modulator, AOM, with the digital confinement of the cloud using a light sheet. If the scanning dipole beam is scanned at a rate faster than the trapping frequencies of the atoms, then the atoms experience the time average of the light potential, so-called time average potential. 3. By careful feedback to the intensity of the scanning beam, we can create a uniform potential. This is then used to study the superfluid properties of the trapped BEC. In order to measure the critical velocity, we will reduce the intensity at a particular point in the scan, generating a barrier, and drag this barrier through the BEC at varying speed, measuring the resulting BEC fraction and temperature for evidence of frictional excitation. The advantages of this method include a very homogeneous potential, which in turn leads to a uniform speed of sound in the experiment and a constant speed of the obstacle that is dragged through the condensate. We are at the preliminary stages of this work but have successfully demonstrated a line trap. See figure 4 below. physics.uq.edu.au. And the data is going to continue in our next video. Thanks for watching.